Dice Esteban que es la persona más virtuosa.
¿Me digo qué? Yesterday I realized that it was a few days back when I was working in the Postgraduate Center, right? It's 6 years.
¿Y qué es un grafo?
It's 6 years have passed.
No te dice por ahí el memo, el código.
Time is flying.
¿Cuánto es para eso?
No te dice por ahí memo, el código, ¿eh?
Yes. So is there a direct frame of time?
No, no hay nada.
Es tan fácil, solamente
Una de 5 centavos.
Time is at rest.
Estaba buscando la vez. Un centavo de como están programados, seguro ya está grabado.
Bendita verdad. Bendita verdad.
I'm bored, I don't watch movies.
Solo tenía.
Aquí tengo pero en la cuenta tenía 12 que son inaccesibles porque tuvimos 20 por semana. Y a mi patrimonio también 15 euros.
Ah, me quedé en esa noche.
¿Me lo puedes pagar con tarjeta?
Sí,
¿Vas a Burger King? Ay, pues, no,
Is there any question about the stress energy tensor? Did you look at it?
We didn't see. We haven't seen it yet. Ah.
No. Okay, so yeah, one thing that I wanted to mention that I usually include these questions with a little asterisk next to them, like that means that it's a bonus problem, so we are not going to cover it in the lecture, so it's for you. If you like, you can think about it. And if you have questions, you can ask me. Also in the homework, if there is that sign, that means that you don't need to write it. Or if you like, you can. It's extra. Okay, so today we are going to talk about the representation theory of Poincare group and see how different particles with different spins arise from looking at the representation a Poincare group. So these are some ideas which are at the core of relativistic quantum field theory or particle physics. So they are very, very important. However, it's a little bit hard to talk about them here. So I mean, I try to explain the main ideas, but you are encouraged to look at the notes and the reference. Okay, so what we discussed was in special relativity, not the symmetry of a space-time is the Poincare symmetry, translations plus Lorentz symmetry. And now we want to talk about a quantum theory that is invariant under these symmetries, or built out of these symmetries. So what we have in quantum mechanics, what we talk about is the wave function. And when you have some symmetry, that symmetry acts on the wave function. When we square the wave function, we get a probability. So these are probabilities for different processes. So in order for the transformation to be a symmetry, it shouldn't change the probability. So probabilities for different processes is a scalar quantity. Different observers can agree on whether some process happened or didn't happen. Therefore, the symmetry transformations should act on the wave function in a special way so that they preserve probabilities. But there are two possible ways. Either they are unitary and linear, or they are anti-unitary and anti-linear. But I don't discuss the second option. So I only consider the unitary representation. So what it means is that if I have some symmetry transformation or symmetry group G, and I consider an element of this symmetry group, think of G as being a group of rotations. And little g will be some particular rotation. If I do this rotation, the wave function changes under the rotation. How does it change? It changes by the action of some unitary operator that is related to this group element on the wave function. And now, for instance, in the case of a group of rotations, we are talking about a continuous group. So we can talk about rotations which are arbitrarily close to zero, to no rotation. So if G is the unit element in this little g is 1, which corresponds to doing no rotations, then that U will also be 1. And again, these rotations, we can talk about infinitesimal rotations, so we can consider elements which are very close to 1. So we can consider the theta that are much, much less than 1. And in that case, the U of theta can be expanded around unit. So we can write it as 1 plus I. Now imagine the group has, based on the dimensionality of group, we might have a number of parameters. Like if I have rotations, we can talk about rotations along Z, along X, or along Y. So there are 3 angles. So this theta doesn't have to be a single parameter. There can be number of them. And these unitary representations can be expanded around theta equal to 0 plus order theta squared, where this is just a unit operator, and these t's are called the generators. Now, when we have a group, when we consider different elements of the group, they have some composition. That's basically part of the definition of the group. That what is when I multiply G1 times G2, that is also an element of the group. Now, when we talk about representations, the condition that they have to satisfy is that if I consider U of G1 and U of G2, if I multiply these two, they have to give the representation of the G1, G2 element. This is basically the definition of the representation of a group. So it has to respect the composition of a group. Now, given a particular group that we have, like group of rotations, this composition rule implies some commutation relations between the generators. Now, again, the familiar example is the group of rotation when TAs go to LIs, the angular momentum operators, and the composition rules of rotations that imply some commutation relation between the angular momentum operator, which is Li, Lj equals I epsilon ijk Lk. So where does this come from? We can just consider a sequence of rotations, a rotation along one axis, and then followed by a rotation along two axes. Let me draw diagram. So 1, 2, 3. So we can consider a small rotation in the 2-3 plane, which means theta 1, and then followed by a small rotation in the 1-3 plane, and then followed by minus theta 1, followed by minus theta 2. If I do this sequence of rotations, that gives me another element of the group, which is second order in theta. Now, if I ask these representations to reproduce the same element, I will get this commutation. Any questions so far? Okay. Okay, now what we are dealing with here is a bigger group, the Poincare group. It includes rotations, but there are other symmetry transformations. So now we are considering members of Poincare group, which is shown on ISO 134 dimension. Now, if I consider some representation of this, it can be transformed or it can be decomposed again in terms of the generators. So there are small translations. I'm considering an element which is which is close to unity. So there are translations whose generators we call P mu, and there are Lorentz transformation. Now again, the composition rules of Poincare group, these are known. Basically, that's the part of the definition of the Poincare group that implies some commutation relations between these generators. So for instance, the commutation of the momenta is equal to what is it? 0. Yeah, so these are translations, right? So two translations commute with each other. Unlike two rotations. And then there will be commutation relation of translations with rotations. I've already done it here. I could have given it as an exercise. So let's consider one special example, just to get an idea. Imagine I want the commutator of say I want the commutator of P1 and J J23.
Should be 0.
Why?
The three is the plane in the x-axis on the one. The 3 is a rotation. J23 is a rotation in the plane on the x-axis.
The perpendicular plane to the momentum.
So it's like the same.
It's invariant.
You rotate around that. And then you go and do what is saying that's going and then rotating.
Yeah. So J23 is doing a rotation in this plane, right? So this is J23, or maybe the other layer. A rotation in 2-3 plane, which is equivalent to rotation along one angle. And P1 is a translation along one, and these two clearly commute with each other. What about, so what else can we look at? Let's say if I look at P0 and J03.
Rotation defined for the time. J03.
So yes, what is J03? So these epsilon omegas are supposed to be elements of Poincare group. Epsilons are just translation. So epsilon mu, there are 4 indices correspond to 4 possible translations. Omega mu news correspond to Lorentz transformation, right? So in particular, if I look at omega ij components, those correspond to just rotation. And then the components that contain 0 correspond to Lorentz transformation. Well, correspond to boosts in this sense. So what does J03 do? It's a boost along Z direction. Okay, so I'm doing a boost along Z direction, and then I have P0, a translation in time. Let's try to do the following. If I wanted to do a finite boost along Z direction, so imagine I only consider one particular element, U, let's call it V, which is a finite boost, not an infinitesimal, a finite boost along Z direction. Then that would look like what? It would be something like, let me don't call it V because it's 150. But let's just look at this element, e to the I beta J03. So this is some finite boost along Z direction. Now, first of all, one question that we can ask is that what is the velocity that corresponds to this boost? So that given a value of beta, there will be some velocity. Because if it's a boost, we know how to relate boost to velocity. Now I have defined it in this way. There should be a relation between beta and the velocity of this boost.
Like hyperbolic tangent to beta, right? Because it should be the relativity.
It should be, but maybe we can derive it. And okay, so that's one question. The other question to ask is that, well, to be honest, this question is not very well defined. If you think about it, because I haven't really fixed something. I can always change the normalization J. The second question that we can ask is that now that we know what is a finite boost, we can act on it on a translation generator. So I can consider U1, U inverse of beta, P mu, U of beta. And if this is a finite boost with some velocity v, we know how it acts on say P0. This will be just gamma of v. What will be P0? It's gamma of v. P0 plus v times P3. Now, in in order for this equation to be valid, there has to be a particular commutation relation between J03 and P0. Because now I can consider a small beta and linearize this equation. So when beta is much less than 1, then when I linearize this equation, I get what I get, something that very depends on the answer to this question. So once you answer that and then linearize this in beta, we understand what should be the commutation relation.
Why do we require this equation to hold?
This one?
Yes, u minus 1 p naught
This is basically the requirement that we are constructing a representation of the group. Is basically this requirement. The fact that well, here we are saying that this U is a generator of a boost, and then in quantum mechanics you have two ways. So when you have symmetry operators, we can act on the states, or we can act on the operators. So if we want to act on the operators, some operator, so if psi goes to u times psi, then if I want to act on the operators go to u inverse or u dagger, it's the same thing. Well, now my O's look like U's. U dagger U. So now what is, for O, I'm taking it to be a 4 vector. And I'm just using the fact that a boost acts on the p mu, but this is just a momentum 4 vector. So that's how it acts on the.
Why should a 4 vector transform like an operator?
Because we're still classical here, right? We haven't made the transition to quantum.
Right. I mean, yeah. Why am I not using u times psi? Like the state vectors. Why am I using this?
Well, it depends. You can do either of those. You can do. This is your choice. You can either transform the states and keep operators unchanged, or keep the state unchanged and transform operator. These are the two Schrödinger pictures.
I'm asking about the 4 vector p. Why is it transforming like an operator?
Well, because it is an operator. So this U is an operator, right? U is.
Okay, yes.
It is a unitary operator that acts on the wave function.
Okay. Yes.
Right. The wave function is a vector in the Hilbert space. U is an operator that acts on this. The group element is specified by a set of numbers, epsilons and omega. Given this set of numbers, given this set of numbers, you construct the unitary operator. Now the generators are Hermitian operators that allows you to construct unitary operators. So P is also an operator in the Hilbert. Yes.
It's like because P is like a generator of the group transformation, but it was originally like in the whole group, in the weight of, it's like in this case, because it's a unitary operator, B is B, the B. B is e to the something, yes, and because it's a unitary operator, we can expand this B as 1 plus I times the generators, and that's what we are doing there.
Sorry, what equation are you talking about?
That I mean,
This?
yeah, I mean,
Uh-huh.
so I say that doing that is because you are making a similarity transformation. I mean, the group element transform on the group with a similarity transformation. So because we are applying this similarity transformation under the group, but then we are changing to like the infinitesimal level, then that is why you are and the P0 or the P mu transform like with that. I mean with the expression like that.
Uh,
With with
no, I
mu
didn't
inverse
mean to
P.
say something very complicated. Um, I was just saying that I'm doing a boost which acts on a 4-vector zeros component of a 4-vector. So we know how the boosts act on 4 vectors. That's how they act. That's all I was saying.
No, it's because I also understand the question why it transforms like that. But I think it's because you, I don't know, you maybe it's like the operators on the group transform like with the adjoint or something, or the generators of the group are transforming with the adjoint, and then that is why the generator is like in the Lie algebra P0 is like a TA. So when you the when the when you something transform with adjoint, it transform with G TA G inverse.
Yeah.
So that is what more or less what is happening right now, I believe.
Is it related to that? I don't think so.
And yeah, and this T and then adjoint the TA go to another TA. In this case, this P0 is going to another P0, but after applying the group transformation. It's because the generators transforming the adjoint representation.
I mean, why would you want to do this transformation? And this transform exactly because this is an operator, and it comes from the probability conservation.
As well. I mean, you can see
right.
Also that, yeah.
Well, I don't understand what you're talking.
Yeah.
I mean, yeah, you can transform the states and apply it to the operator and transform the operator.
Yes, it's right.
And yeah, it's the same. I mean, for
Is it P3? The result P3.
The result of this? Yes, it is P3. I mean, I guess it's just here. If I expand this transformation, so if I can say e to the I beta minus I beta J03 P0 e to the I beta J03, then we can write this as P0 plus I beta commutator of P0 J03 plus higher order terms. So if I just compare these two, provided that we find the relation between V and beta, then we can match. But it's already clear that the commutator of P0 and J03 has to be proportional to P3. The proportionality coefficient can be chosen such that, the normalization of J03 can be chosen such that the proportionality coefficient is 1. So that's when I choose that proportionality coefficient to be 1, then this question is also well defined. I can fix what is the relation between velocity and beta parameter. But the fact that I write it p mu and call it momentum is it has a reason. It's related to the Noether theorem that we discussed yesterday. So if we calculate the conserved current corresponding to translations, that is the stress energy tensor. When we integrate it over the space, that gives us conserved charges, and conserved charges corresponding to translations are momentum. Is the four momenta. The four momenta. And then we can show that this is one of the exercises. We can show that the conserved charges are the generators of the transformation in the quantum field. So this P is not a coincidence that I call this P. It's actually the conserved charge associated to the translation. Okay.
But I have a question.
Mm-hmm.
I mean, when you define the general U, just define in general that there is a parameter theta A and the generator PA.
Mm-hmm.
But when you were defining this Lorentz group or Poincaré group, why did you have? I mean, why did you choose two different parameters and two different generators? What was the motivation behind it?
Oh, that was with some hindsight, because we talked separately about translations and Lorentz transformation. In principle, I could define a new index that I could define some vector theta that is composed of epsilons, from epsilon 0 to epsilon 3, and then omega 0, 1, omega 0, I, and omega ij.
Yes. Okay.
I just separated them because they have different meaning for us.
Okay.
And then in the rest of the discussion, we want to treat them slightly differently. For instance, the commutation relations, so P's all commute with one another, while J mu's do not commute with one another. Okay, what do P mu's do with J mu sigma? That can be guessed essentially using the symmetry. So this is this can be nothing but P mu eta mu sigma minus P sigma eta mu nu. Just because it has to be anti-symmetry on the exchange of nu and sigma. So that's the reason for this minus sign. And then the normalization coefficient is fixed basically by redefining this variable omega. The sign isn't the same sign. I guess here I have the opposite sign. And then J mu nus have a commutation relation which is more complicated, but can be derived using the same idea. Well, in fact, it can be almost fixed up to the normalization constant. It can be almost fixed by just the symmetry properties, just using the fact that using the symmetry properties of J's. Okay, so I won't write this. No, so what do we want to do? We want to find the representations we want to find the irreducible representations of these Poincare groups. So what does it mean? We want to do something similar to what you're familiar with in the non-relativistic quantum mechanics. When we were talking about when we talk about the rotation group, the algebra of angular momentum operators, we find irreducible representations of SO3 group, the group of rotations, and that gives us the notion of a spin. So we can label different particles by different values of the spin. So here we want to do a similar thing. We want to see what are the possibilities for labeling degrees of freedom in a relativistic quantum theory. So in order to do that, we have a bunch of symmetry transformation, a bunch of operators. What we do is that we first diagonalize as many of them as we can. In the case of rotations, we could not diagonalize all of them, so we would diagonalize just one LC and the total angular momentum, L squared. Now here we follow something similar. So first we notice that, and another point is that usually we would like to diagonalize the Hamiltonian. We want to see what are the energy eigenvectors. So P0 would be, Hamiltonian is the generator of time transition, would correspond to P0, and all momenta commute with P0. So we can simultaneously diagonalize all of them. So first we take, we diagonalize P mu, and therefore we label the wave functions by a 4-vector little p, so that the operator P mu acting on psi gives me P mu times psi of P and sigma. Oh, this is capital. This is the operator. This little p is the one that is the index of my wave function. So I have psi's with different values of p's. Those correspond to states with different center of mass momenta. So I can diagonalize this momentum operators. Now we need to take care of. Okay, before that, I should talk about sigma. So sigma is supposed to be supposed to correspond to all other labels that distinguish different particles. Like in non-relativistic quantum mechanics, you can imagine again momentum and the spin of the particles. So the sigma can be something like that. Now you can ask, can sigma be continuous, another continuous level? Because as you see here, P is the center of mass momentum and it is continuous. Variable. Under boost, I can continuously change the P mu from one value to the other unless it is 0, which corresponds to the vacuum. Now one question to ask is that are these remaining variables, can they be continuous variables or they are discrete like a spin? In principle, they can be continuous. For instance, imagine a two-particle state. Well, I guess when I talk about two-particle states, I'm going a bit ahead of myself. But I think I understand what I mean. So if I consider some two-particle state, the total system has a total value of energy and momentum. That's what we call center of mass energy and moment. So there will be some P total, which is, so this is particle 1, particle 2, it is P1 mu plus P2 mu, right? So total energy and total momentum of the system. That's essentially what we call P in this case, because if this wave function is supposed to be a two particles, this P when acts on the total translation only cares about the total energy momentum of the system. So that's this P. However, the system, there is of course there are two form momenta, so there will be also a relative momentum, or relative velocity of this particle. So this relative velocity of the particles is a continuous label for this system. So if you imagine these are free particles, if they are boundless, then no, it's not up to us to continuously change the relative velocity of two objects. There will be discrete levels like hydrogen atom. But the moment we consider free particles, then there will be relative velocity, and that is another continuous label for the system. If we consider more particles, there will be even more continuous parameters, because now we have more and more moment. So in principle, it is possible that these remaining the remaining indices are continuous. However, what we are interested in is to determine something like the notion of single particles. So it's essentially, you can think of it as a definition. The definition of single particles are the ones that they only have one continuous label, which is just this total P mu, and the rest are discrete.
So those are quantum numbers?
Sorry?
Like the sigma can be quantum number? Like
Yeah, like a spin. Yeah. But another thing that we see is that even there is some exception to this rule, but it's kind of an exotic exception. So as you see, there are some representations that correspond to particles with continuous spin, and so for those, the sigma variable will again be a continuous variable. But at least empirically, those representations do not seem to exist. We haven't seen anything like that. So for the moment, let's ignore those. Okay, so we want to take this sigma to be discrete. Now, let's consider, okay, so we took care of translations. Now we have to talk about Lorentz transformation. So we want to see how a Lorentz transformation acts on a state with some specific momentum. So the same question that we asked in the case of rotation. To understand how a general rotation acts to the state, what we do is that we decompose the state in terms of the different different representations of rotation group with different spins, and we know that how rotation group acts on any individual rotation. So first of all, what we can notice is that when I act by boost on the state with definite momentum p, then it changes the momentum, which can be seen by acting by the momentum operator on this new state. So this can be written as U of lambda, U inverse lambda P mu U of lambda times psi of P and sigma. So I just multiply unity. This is just unity. U of lambda, U inverse of lambda. To the left of P mu. But this combination is exactly what we discussed 5 minutes ago. This is just the Lorentz transformation acting on P mu. So it is U lambda times lambda mu nu times P nu operator acting on psi of P and sigma. The P nu acting on psi gives little P nu. So what we get is lambda mu nu, little P nu. Now this is a number, so we can just commute it and take it to the left, and then the operator U lambda acting on psi of P and sigma. So what it means is that if psi is the eigenstates of P operator with momentum with eigenvalue little p, then U lambda acting on psi is the eigenvalue of P mu operator with eigenvalue lambda mu nu times, which is basically what one should expect. If I boost the state, I have to boost its moment, center of mass moment. So this state U lambda psi P sigma can be expanded in terms of states with momentum lambda p, but possibly with different, will be a superposition of different states with different discrete quantum numbers. All that we know is that the momentum of this state is lambda p. Therefore, I expand it as a linear combination of states with lambda p. Okay, so now what we are looking at is that this D matrix is it can have some block diagonal structure, and that's what we mean by irreducible representation. So if it has a block diagonal structure, what it implies is that under general Lorentz transformation, these different sigma levels only rotate within some groups. So that's why we call them irreducible representation. If I have two of these blocks within these sigmas, I can just separate them. They don't mix with each other under Lorentz transformers. So essentially the goal is to understand what is the structure of this D sigma prime. Now to do that, the trick is to introduce a notion of little group. So what is what is the notion of relativity? How do we find the irreducible representation? Any questions so far?
So,
yeah.
If I apply U over the third side,
Uh-huh.
this could decompose in a linear combination of the other, but of several sides that label each one by sigma prime without different sigma. For example, if I have a spin 1 particle and expanded other spin 1, 2, 3, does it? Because I'm zooming over sigma prime.
Yes.
Okay.
I'm saying that all that we know at the moment is that U lambda acting on psi of P and sigma has momentum lambda P. That's all that we know. Therefore, it has to be a linear combination of all of this. This is the most general thing that I can write.
But over different P.
No, the same. They are all the same P.
Different lambda P.
It's a Lorentz transformation.
Like the lambda is fixed and P is fixed. Now I'm saying if I act by U lambda on this side, the momentum of this state is also fixed to be lambda P. That was they say the purpose of this exercise. But this shows that the momentum of this state is lambda P. Therefore, it is a linear combination of all of the states with momentum lambda P. And that's what I have written.
But each of one has a different sigma.
Well, they can, yes, because I'm writing a linear combination of all of the states. So when I fix lambda P, I still have different states corresponding to different values of sigma. Maybe, I mean, again, let's go back to rotations. If this lambda is just a simple rotation, what does it do? If I have P along one axis and do a rotation along 3 axes by pi over 2, what happens is that lambda P will be now a momentum along y-axis, right? But also this rotation, if I'm talking about particles with different spins, this rotation mixes different eigenstates of spin z, for instance, operator. Like if you use if sigma labels if sigma can label, for instance, in that particular example, sigma can correspond to S total and the z component of it, right? Now, if I do a rotation, I'm going to mix different states with different value of SC, unless the rotation is along Z, which is what I said. But say I do a rotation along X, for instance.
Why I have to zoom over all of them?
Yeah. Right, when I use, for instance, SZ to label my states and do a rotation along X, I'm going to mix all of the states with different values of SC. But they're still within the same S total. So that S total corresponds to different irreducible representations. Those with different S total will not mix with each other. But within each of them, the different SCs mix with one another. Okay, so this is non-relativistic story. It's simpler in the non-relativistic case because the boosts do not commute into rotation. So if I want to consider some general transformation, the decomposition in terms of rotation is always unambiguous. It wouldn't matter how I write the general transformation. Therefore, I can separate the discussion of boosts from rotation. In the case of Lorentz, it is a bit more complicated. but not too complicated. So the method to find this irreducible representation is to consider, to define some reference momentum k, and say that take psi of p and sigma to be some normalization factor np times, so take a reference, a standard Lorentz transformation L of p and a standard momentum k, as so that L mu, Lp mu nu acting on k nu is p mu. So this L can be just a pure boost, for instance, the way we introduced it before. So just a fixed, it doesn't matter what it is. It has to be just a fixed transformation. So I fix some family of transformations so that for any momentum, and I fix also k, some standard moment. And then for any p mu, there will be one of these standard transformations or standard boosts that take me from k to p. Then I take this psi of p and sigma to be the unitary corresponding to that L of p acting on psi of k and sigma. So far it's just a definition. This n is just a normalization constant or number, and this u is the unitary corresponding to this standard transformation. Now let's ask what happens if I act by a general u lambda on this psi p sigma.
But I'm a bit confused about this L. Is it different from lambda?
It's a very particular choice of lambda is a general Lorentz transformation.
Yes.
L is a predefined, a fixed Lorentz transformation. So it's not an arbitrary one.
Okay.
Because, okay, so let me give you an example. It will become kind of more clear when we consider the concrete examples. But you can imagine many ways of going from k to p.
Yes.
So once you fix k and you want to do a Lorentz transformation that takes you to p, that is not a unique transformation. For instance, if k is a particle moving along one axis, and p is particle moving along two axes, x and y,
yes,
then L can be a rotation along z that takes you from x to y.
yes.
However, it can also be a rotation along x, and after that a rotation along. That also takes you from k to
yes.
p. So it's not uniquely fixed. What I'm doing here is that I'm fixing a standard set of transformations. It's a subset of transformations which I fixed from the beginning.
Okay.
While this lambda is general, so I can say general lambda that acts on psi. Now what do? I just plug in this definition here. And what I can do is that, as usual, I introduce u L lambda p, u inverse L lambda p. So I insert basically the unit operator to the left of this u lambda. So this was just a unit operator. On the other hand, this object, now let's look at the composition rules of the Lorentz group. This is a Lorentz transformation L, and then a Lorentz transformation lambda, and then a inverse Lorentz transformation with L of lambda p. So what does it do? This L take me from K to P. So that's L of P. Lambda take P to lambda P. And L of lambda P takes K to lambda P. Therefore, U inverse of L of lambda P takes lambda P to K. So this whole thing, I can call it W. This composition Lorentz transformation, I call it U of W. W is a Lorentz transformation that takes K to itself. So I have N of P, U of N lambda P, and then U of W acting on psi of K and sigma. And again, we can write this this object, we can expand it in terms of this D. So let's write here N of P. No, but yeah. Okay, so U is acting on psi of K sigma. That is, again, that fixes K. That doesn't change K. But it will, again, like here, it will be a linear superposition of all the states with momentum K. So this U lambda times psi this sigma, it is N of P U of L of lambda P times a linear combination. Now let's call it this matrix D tilde of sigma sigma prime psi K sigma prime. Or maybe a better thing to do is that label this D by lambda, and then call this D of W. Okay, now I can take this inside and then use the definition. Use this definition. So what it tells me is that I have N of P divided by N of lambda P, sum over dW sigma sigma prime. And then this axiom psi just gives me psi of lambda p and sigma prime. So now we have found these matrices D of lambda, sigma sigma prime. These are just np divided by n lambda p times d sigma sigma prime of W. So if we find the irreducible representations of these transformations, W's, which preserve the momentum k, we have essentially found the irreducible representation of Lorentz. We are done. We have found this D. So that is called the method of induced representations. And this subgroup of Lorentz transformation that preserve K, they form a subgroup which is called a little group. Now we can consider some examples too.
Sorry, why is how does it prove the n lambda p?
This one, I just use this definition.
Okay.
Okay, so what the task would be that we choose the reference momentum and then find what is the little group. So we fix K mu. That is arbitrary, but some choices are better than others. Once we fix that, then the second step would be to find W, the subgroup, which is a little group. With the property that W mu nu K mu is K mu. Once we do that, then we find these are basically representations of W. So for instance, we can consider so as you saw here, we labeled the states with some momentum, and Lorentz transformation can change momentum, but of course they won't change the norm of momentum. They won't change p squared. So p squared is preserved under Lorentz transformation. So then we have two possible choices. Two possible reasonable choices. When p squared is minus some m squared, so we are talking about a massive particle. In this case, the good choice for this K mu reference momentum would be to go to the rest frame of the massive particle.
Yes. So, sorry, how did you get the d lambda?
Oh, I compared this equation with this equation.
Okay.
Okay, so in this case, we go to the rest frame. I mean, that is a convenient choice. Then K mu looks like m and 0. So what is the subclass of Lorentz transformation that preserves this momentum?
Rotation.
Yeah. So in this case, this little group is just rotations SO3. And then we know what are the representations of SO3. These are just particles with a spin, integer or half integer. And these matrices also we know what they are. These are exactly the same matrices that we had in non-relativistic quantum mechanics. The only thing that changes in this story is that there are these normalization factors when we go for consider general lambda. The novel case, which doesn't have an analog in non-relativistic quantum mechanics, is the case of massless particle. So if p squared is equal to 0, then we cannot go to the rest frame. Instead, we choose k mu to be some other reference moment. Say k mu is a momentum which has value 1 electron volt and points along x direction. So every momentum can be brought to this k mu by an appropriate Lorentz transformation, right? Of course, we have to fix what is our differential L. So there are many possible ways of bringing an arbitrary p to this. You have to fix one of them, but I can give you one of them. Just for any, so let's say p mu is 10 electron volt and points in some arbitrary direction. So it's 10, 1, and some p hat. So what we can do to bring k to p is that we first do a boost along one direction so that it blue shifts. Its momentum, its frequency becomes 10 instead of 1. Then we can do a rotation that takes one axis into this p hat axis. There is always a rotation. There are many rotations. So we pick one standard one that takes x axis into p hat. So this is possible. We can do that. Now the question is what is the subgroup of Lorentz transformation that preserves this momentum?
Rotation in those two planes?
Yeah, that is so one obvious one is that if I do a rotation into 3 plane, that doesn't change this momentum. So that is definitely an element of the little group. J23 belongs to the this little group. But I can do more. So imagine I do a boost in the 0-2 direction. So let's consider some infinitesimal boost in 0-2 direction. So then what happens? The parameter, what do we call it? Some little omega. Then I will have this k prime. So if I linearize in omega, then so we are just doing a boost. K0 prime is going to be K0, and K2 prime, K prime 2, is going to be omega times K0. K prime 1 doesn't change, it's just K1. Right? So I'm just doing an infinitesimal boost. So I'm ignoring order omega squared correction. Okay, so this obviously doesn't look like the original one, it looks like this. So now K prime mu is equal to 1, 1, and omega, and 0. So that's order omega squared correction. However, I can combine this with the rotation in 1-2 plane. So if I do a rotation in 1-2 plane, I can bring this back to the original form. So now let's do J12 with parameter minus omega. What it does is that now K second 0 remains the same, and second 1 remains the same. Second 2 becomes prime 2 minus omega K prime 1, which is 0. So this, when I combine these two, I get a new vector which looks the same as before. Again, plus order omega squared correction. Similarly, we can combine J03 and J13. So essentially there are 3 generators of this data group. One is the obvious one, and then there are 2 other ones which are linear combinations of boost and rotation. J02 minus J12, and B is J03 minus J13. And then we can use the algebra of J's to find the algebra of this A's to understand what is this little group.
How did you write these two? Can you please explain this?
So A is what? A is this.
Yes.
The combination of J02
yes.
and J12
right.
with opposite
parameters.
Yeah.
The value of the parameters.
Yeah.
Yes.
So the other one, B, is basically
okay. We can do it the same thing with 3.
Yeah.
Right.
Yes. Now you can ask what is the algebra of these A's, and one can see that A and B commute to 0. A and J, let's call this J now, commute to B, and B and J commute to minus A, I think. And this is exactly the algebra of symmetries of a 2D plane. So if I have 2D plane, if I consider translations around X and Y, that those two correspond to, they are analogs of A and B, and J is rotation in this XY. So this is the 2D plane which is perpendicular to this x-axis. Now one can try to find the irreducible representations of this group. Now, we started from Poincaré, which was the symmetries of 3 plus 1 dimension, and the little group reduced to the symmetries of a 2D Euclidean plane. Now, one can again try to find the irreducible representation of this. Now, what happens is that so these A's and B's again are generators of translations in these two planes. So if we choose the wave function, so there were P. Now let's say there is another label A. So as before, we can diagonalize the translation. So let's say we diagonalize A and B as we diagonalize P's. So similarly for B, A, B, sigma, A, B, sigma. However, what happens is that if A and B, A or B are non-zero, then because of these commutation relations, they have to assume a continuous value. The same way that if I have non-zero momentum, then under rotations, a momentum along x-axis continuously changes to all possible values. So here is the same, a non-zero A under rotations changes into values of A and B, which are essentially related by rotation. So A prime will be A cosine theta plus B sine theta, this sort of relation. So what happens is that these labels become continuous. These are called continuous spin representations. Now we discard them because we haven't seen something like this. Some people have recently reconsidered them. But yes, so the standard, the conventional wisdom is that these do not exist in the nature. A and B are zero. When A and B are zero, we are just left with this simple rotation, SO2 rotation, which is generated by this operator, and therefore sigma will be labeled by the eigenvalues of J. Now, if we use the fact that after a 2π rotation, the wave function has to come back to itself or minus itself, that fixes these eigenvalues to be integers or half integers. So these eigenvalues are, by the way, called helicity. So then for massless particle, we will have momentum and we will have helicity. And helicities, just by requirement that the 2π rotation gives either 1 or minus 1, have to be integer or half integer.
Which 2D plane is it? Is it I mean, we were considering the Lorentz transformations, right?
Mm-hmm.
So, and it was related to the space of the space-time. I mean, it was related to the space-time itself.
Uh-huh.
So, I mean, this rotations, velocity correspond to a rotation to a physical space? I mean, the space-time?
So these were just the subgroup of Lorentz which rotate these 2-3 plane.
Yes.
So this is just, if you choose the momentum to be along 1, these are rotations in the plane perpendicular to 1.
Yes. Okay.
A and B are not real translations of the origin of Poincare group, but uh, the commutation relation, they are analog of the translations in a 2D plane.
But their eigenvalues are 0. I mean, that's found in nature, right?
Yeah, that's what we. I think that's the current status. So
how do
we
you
haven't
measure those eigenvalues?
Well, what we see is that the degrees of freedom don't have continuous labels; they have discrete ones.
Okay.
So you have discrete spins. Like massless particles have a photon; they have two polarizations. They don't have a continuous label.
Right.
Or in other words, if I set A and B to 0, I can describe everything that we already see. I have a standard model of particle physics is based on assuming that A and B are 0, and it explains everything. There's nothing that we have observed and doesn't fit within that. Again, some people who considered it recently, not very recent, like in 2014, I guess. They were considering them as a candidate for dark matter, because we haven't seen dark matter, but we want to consider different possibilities for dark matter and see what kind of signatures they have, so that we look carefully for those signatures. So those people were considering this as some possibility for dark matter. They had some troubles for even constructing an interacting theory for these particles. So here I have only talked about what are the allowed representations. That by itself doesn't necessarily guarantee that there is a reasonable theory, interacting theory for that representation. In fact, in many cases, I think it's almost proven that there is no reasonable theory for many choices. Like if I go to higher spins, or there are very limited choices in which these higher spin particles, for instance, they come together in a very special in a very particular form. So far, you just think of it as the list of possibilities, just allowed by group theory, by representation theory.
And the physical definition of helicity that we know is that the projection of the spin along the direction of the momentum. And how is it related to this picture? Can you just show this?
For massless particles, that's exactly this. That projection of a spin along momentum coincides with what I call H. For massive ones, it's what you said.
Yes.
So if I consider a particle with helicity 1, and I look at the projection of a spin along momentum, I always get 1. Yeah.
If there were like these continuous spin states, you could, even for massless particles, you could like flip the velocity. Could you do it?
Flip? You mean going from 1 to -1?
applying like A to the spin or something like that.
Let's see. Well, in that case, I wouldn't. I guess they are not. But first of all, I should say that I haven't studied those very carefully, so I'm not sure. But secondly, I think there you have to label particles not just by helicity. So there are these A and B variables too.
Yes.
Now whether I can. Yeah, I'm not sure. I don't know.
Basically, this is more or less like when we talk about groups. This is like finding the cartan and building up the rising and lowering operators to diagonalize your I mean finding the final the basis of the representation, more or less.
I don't know.
I don't know if I explained.
Okay, the class is over.